Hello everyone, welcome back to Trigonometric Substitution. Now we're going to attack case 2, where we have a difference of square of the form k squared, so k is a constant, minus f squared, where f is some equation involving x. So when you have a difference of square and you are setting up your right triangle, so same picture, same right triangle, theta is at the base. Here we need to define an opposite side, an adjacent side, and also an hypotenuse. So when you have a difference of square, the hypotenuse is always going to be the first term. So here k is going to go inside your hypotenuse. But now what about f? F could go at the opposite side or could go at the adjacent side, but the easier trigonometric substitution is going to happen if you choose the opposite side for f. The way I like to think about it is that in your case 1, f was at the opposite side, so I'm basically just leaving it there. So the only one that moves around is k. K has no choice to go to the hypotenuse. And now the missing side is always a side that you have to compute. So remember, there's always one side that you are computing using Pythagoras' theorem. So using Pythagoras' theorem, the adjacent side is going to be k squared minus f squared square root. And of course, this is good. The inside of that square root matches your difference of square. So this is how you know that your right triangle is set up correctly. Always make sure that the right triangle, so using basic geometry here, is set up such that by computing the missing side, you're getting back your case difference. So in this case, by computing the adjacent side using Pythagoras' theorem, hypotenuse squared, k squared, minus the opposite side squared, f squared, square rooted, gives you a square root where the inside is your difference of square. And now here we go. So the first thing we do is we need to create a ratio that links f and theta. So f is at the opposite side, and we always want to use the easier side. So again, here the star side and all these things are involving the constant. The constant is like the easier thing to manipulate here. So if we want to create a ratio that involves the opposite side and the hypotenuse, for case 2, you're always going to be using a sine ratio. So here sine theta is the opposite side, which is f, over the hypotenuse, which is k. And at this point, as usual, if you want a formula for theta, if you want to extract theta out of that sine, you're going to be using an arc sine on both sides. So arc sine of sine they cancel each other. And then on the right side, you get arc sine of f over k. Yeah. So if needed, we have a formula for theta. The second step, purely computational. First, you find a formula for f. So if you multiply k on the left side, you get that k sine theta is equal to f. Then you compute the derivative of that equation. The derivative of k sine theta with respect to theta is k cos theta d theta. And then on the right side, the derivative of f with respect to x is f prime dx. So we have a formula for f, and typically that formula for f will give us a way to find a formula for x. And then by computing the derivative, we get a formula for dx. And we need that formula for x and dx out of the formula for f and dx. And then the star of my style that I really enjoy is creating a ratio for the square root, the difference of square here. So for the difference of square, so this k squared minus f squared and theta. So again here, you want to use or set up a ratio that involves the adjacent side. So we want a ratio for the square root. So the square root is at the adjacent side, and we're always going to be using the hypotenuse because it's k. So a ratio that involves the adjacent side and the hypotenuse, you're always going to be using a cosine ratio here. So here cos theta, so it's adjacent. So cos theta, so it's k squared minus f squared. So that's my adjacent side over the hypotenuse, so over k. And if you isolate the square root, you get that k squared. So just by multiplying by k here, you get k cos theta is going to be used to replace the square root of k squared minus f squared. Always, always. All right, and this is all you need to set up your case 2. Again here, in the case 2 scenario, so when you have a difference of square, the first term, which is k squared, tells us you have no choice here. K goes at the hypotenuse. For f, the best place is at the opposite side by using Pythagoras theorem. The adjacent side is the square root of k squared minus f squared. If you want a ratio for f, then you're going to use the opposite side in the hypotenuse. So sine theta is f over k. You can compute the arc side on both sides to get a formula for theta if needed. If you isolate f, you get k sine theta. If you differentiate, you get k cos theta. D theta is equal to f prime dx. Very useful formulas, computed and really derived from the first ratio that you set up. And then setting up a ratio for the square root is going to help you simplify your integral greatly. So for the square root, you're going to use adjacent and hypotenuse. So the best ratio for that is cosine. So the square root of k squared minus f squared over k. If you isolate the square root, k cos theta is your formula for the square root of k squared minus f squared. So this is the setup, and this needs to be done perfectly well organized in order to move forward. All right, let's do an example together of a case 2. All right, let's do an example. Let's integrate the square root of 4 minus x squared. Again, if you try a substitution, not going to work here. The inside of the square root gives you a derivative which is minus 2x, and so multiple of x that you don't have. So substitutions won't work. So, but what we see here inside is a nice difference. I have 4 minus x squared. So that's a nice difference of squares. So the constant is first. So boom. Okay, so this is a case 2 problem. So case 2 where you have a difference of square. So here the 4 minus x squared, just to make sure that you see it. So 4 is 2 squared, and x squared is, of course, x. Kind of overdoing it here, but just to make sure that you're going to set up a right triangle that is actually correct. So here in a difference of square, the first term, which is 4 or 2 squared, so 2 is going to be your hypotenuse, and x is going to be your opposite side. You could put it as the adjacent side, but it's going to be easier if you put it at the opposite side. Now, by using Pythagoras theorem, I'm not looking at my integral. It looks like I'm assigning it, but I'm not. So you're computing the missing side. So the hypotenuse squared, so 2 squared is 4, minus the opposite side, x squared is x squared. So by using Pythagoras theorem, the square root of 4 minus x squared is the adjacent side. And now you're ready to first set up a ratio for f. In this case, f is just x. So you're going to use sine theta. So sine theta is opposite over hypotenuse. And I strongly recommend that once you have your ratio for sine theta, that you isolate theta if needed. So by computing the arc sine on both sides, you get that theta is arc sine of x over 2. So that's your first ratio. Remember now the second step is purely computational. Let's isolate x by multiplying by 2. So we get 2 sine theta is equal to x. Now you differentiate 2 sine theta. You're going to get 2 cos theta d theta. The derivative of x, it's a bit redundant here, but just to really see it, the derivative of x is 1 dx. So I'm going to use the dx here for my formula at some point. Purely computational here, isolate x, compute a derivative, you get your step 2. And then step 3, let's set up a ratio for the square root. So the square root is at the adjacent side. You're always going to use your hypotenuse here, which is the number. So remember, the hypotenuse is the far side here. So we want a ratio for the square root. So you're going to be using cosine. So here, cos theta is equal to adjacent side, so 4 minus x squared, square rooted over 2. So if you just multiply by 2, you get 2 cos theta is equal to 4 minus x squared. that's all the setup that you need to transform this lovely integral into the following one. So this will become, not become, so let me just rewrite first. So the square root, and here I can see it, the square root of 4 minus x squared. I have a formula for that. It's going to be 2 cos theta. And the dx, I also have a formula for that. It's going to be 2 cos theta d theta. That's really nice. So here we go. So the square root will now just become 2 cos theta. And the dx will blossom into another 2 cos theta d theta. So if you put all the coefficients outside, 2 times 2, that's 4. Cos times cos, that's cos squared, theta d theta. Now you need to integrate cos squared theta d theta. That's a trig integral. So we get a lot of trig integrals in these questions. That starts as a trig substitution. So cos squared. So here the power of sine is 0. So m is 0. And the power of cosine, the n, is 2. So both even. So I need to use a trig identity. So using the third trig identity, I'm going to use an identity here, the third one, the trig identity 3. So maybe I'll just write here trigonometric identity. So cos squared is going to become 1 plus cos. The inside of cos is theta. You double it, so you get 2 theta over 2 d theta. So the power 2 is gone now to a power 1. Now you can take the 2 outside with the 4. So you're getting 2. 4 over 2 is 2. 1 plus cos of 2 theta d theta. Now you're ready to integrate the integral of 1. So let's go to the other side here. So here we go. Let's go here. Boom. Let's draw an arrow. So this will become 2, open bracket, the integral of 1 with respect to theta is theta. The integral of cos is sine of 2 theta, but because the inside is 2 theta, you need to divide by 2 plus c. So you can multiply by 2 now. You get 2 theta plus 2 times sine 2 theta over 2. The 2 will cancel. You're going to get sine of 2 theta plus c. So now you want to replace your stuff. So theta, we have a formula for it. It's going to be arc sine, but sine of 2 theta, we don't have a triangle where the angle is 2 theta. So for that, what you're going to use is the following identity. We know that sine of 2 theta. So that's another useful identity here. Sine of 2 theta is actually the same thing as 2 cos theta sine theta. So it's always easier to work with a theta formula. So I'm going to use this as like a sine note. So if you see sine of 2 theta, this happens a lot. This is how you get rid of the angle to theta, to go back to theta, because I want to use my triangle to get rid of those theta and get nice formulas. All right, so this now becomes 2 theta plus 2 cos theta sine theta plus c. Now we know what theta is. So theta is arc sine of x over 2. So you get 2 arc sine of x over 2. Cos theta, so I'm using my right triangle here, cos theta. So if you look at your right triangle, so by definition is adjacent over hypotenuse. So adjacent is the square root of 4 minus x squared over the hypotenuse, which is over 2 times sine. Sine is the opposite side over the hypotenuse, so x over 2 plus c. And if you really want to, you can simplify this a little bit. I mean, you can leave it like this, but if you really, really want to make this as clean as possible, you get 2 arc sine of x over 2. The over 4 times 2, x will look nicer first. So you get x square root of 4 minus x squared over 2 plus c. And this is as good as it gets for that question. All right, so for case 2, how to set up your right triangle and with a nice example. That's it. That's all. Bye-bye.